Uh, Good evening, everyone. It's a great pleasure to introduce our distinguished speaker of this session, Professor Miguel Bernal, professor at Sonora Institute of Technology, Mexico. Professor Bernal received his PhD in automatic control from the Czech Technical University in Prague in 2005 and has since made significant international research contributions in advanced control theory. He has worked as a postdoctoral researcher in France and has been an active member of the National Research System of Mexico since 2007. Professor Bernal is widely recognized for his research in nonlinear control using convex structures and linear matrix inequalities, leading several international research projects and supervising numerous PhD scholars across Mexico, France, and Spain. He has authored more than 70 journal papers with over 2,500 citations, reflecting his strong impact in the field of control engineering. Today, he will deliver a lecture on convex control for a class of systems modeled by differential algebraic equations. We are honored to have him with us and look forward to an insightful and enriching session. I warmly invite Professor Miguel Bernal to begin his presentation. Sir, please.
Thank you very much. Well, first of all, I will have to say a few words about my university and the research teams that work there. The Sonora Institute of Technology is a small university. It has around 1,600 students, 16,000 students, more or less. And this university has a Department of Electrical and Electronics Engineering, where I work at. And at this department, there are several, let's say, academic corps that actually work in different fields, mainly on energy, like, I don't know, solar cells and stuff like that, solar grids. And there is a control department where I work at. And we have several programs like master degree and PhD degree where students are selected and have enjoyed some scholarship because these programs are recognized by the secretary, by the Minister of Science and Technology. And these programs actually have some exchanges with some other universities, mainly with universities we worked before at, like with France. There are some cooperation programs. There are some others with Spain. There are some others with Brazil. Actually, some of the master students have spent some time down there. And well, this is a small amount of activities, but still it's a young university. And this has some kind of advantages because in a small university, you can actually perform any administrative task in an easier way. So it's not all these advantages in that sense. We are at the northwestern part of Mexico, very close to Arizona in the United States. And this is not a very well place for weather, but it's a very nice place to walk. It's a very hot place. But actually, this is winter and we are around 30 degrees during the day. So you can have an idea of that. Concerning our collaborations with some other institutions, we have run an international program with France. Around 10 students of our programs have spent their time there with a PhD program in France, let's say a dual program. And well, this is the strongest team because convex control, which I'm going to talk about, was actually born in Japan, and then it was developed in France mainly. And some other researchers from Spain and some others from Brazil have also collaborated in this area. This is a very hard to define area, as you will see later, because it came from fuzzy origins, from fuzzy control, and it came also from linear parameter varying areas, but it was all messed up, unfortunately, at the beginning, in notation, in the scope of the research, in the assumptions. And there are some some subtleties that I would like to show you before going ahead. So maybe I will share my presentation already if you don't have any further comments on this.
Yeah, no problem.
Let me see. Okay, here it is, I think. Okay, let's see. Do you all see this?
Yes, we can.
Okay, perfect. Okay, fine. So wait a second. Okay, this conversation, I don't see how to. Okay, now fine. Well, the title of this talk is Convex Control for a Class of Systems Modeled by Differential Algebraic Equations. So first of all, I will talk about convex control. I will talk something about the essentials, the very essentials of convex control, which go back to the 90s and the beginning of the 2000s. And then I will move smoothly to differential algebraic equations, which are the, let's say, the novelty or the technical novelty in this talk. This presentation and the works that I'm going to talk about were made when I was doing a sabbatical leave in Valencia, in Spain, with Professor Antonio Sala from the Polytechnical University of Valencia. So I take this opportunity to acknowledge Professor Antonio Sala for his collaboration. This also has been supported by my own university and also by the Minister of Science and Technology. So I acknowledge these institutions. I also take the opportunity to acknowledge the Indian Control Conference, which I attended twice already in 2024 and 2025. I was always very interested in India as a country, and my first chance to go there was in 2024, and I was delighted. Actually, I really enjoyed, and I took the chance to visit a lot of places. So I really enjoyed the country. I really enjoyed people and the kindness of the conference. It was a very, very nice environment in both of them, in Bhopal and in Bengaluru. So thank you very much. I think the next one is in Kolkata. So I'm looking forward for that. All right, let's see. First, I'm going to discuss a little bit what is this talk about. I will go to the basics of convex control. I will talk about computer torque when applied to differential algebraic equations, which are mainly used to model Euler-Lagrange systems under restrictions. Then I will talk about convex control for these differential algebraic equations, and I will close with something about convex observers for differential algebraic equations, which are the most recent papers that I have published, actually. So first of all, this talk is about convex control. I will tell a little bit more about that for a class of systems model as descriptor systems. Perhaps you have heard these names, descriptor systems, which are the first equation, singular systems, where the left side matrix E of X is singular or not invertible in a domain, or differential algebraic equations like the equations at the end of this slide. All of these names, descriptor systems, singular systems, and differential algebraic equations have been used indistinctly in several places, leading to some confusion, actually. A descriptor system usually is a state space representation as described above. If E of X is invertible, you can get an ordinary differential equation, an ODE. But the problem of doing this is that you will obtain more conservative results, as we will see later. If you have E of X, which is not invertible, usually you have some parts which are differential equations and some parts which are algebraic equations. But if you preserve the structure above with E of X, then you will not be able to obtain some of the results I will talk about later. So I prefer the representation as a differential algebraic equation last at the end. So you have n equations, which are differential equations, which has some differential variables, x1, And you have some algebraic equations, like at the bottom, g of x1 and x2 and u, where x2 are called algebraic equations or algebraic variables. So you have q algebraic variables, you have n differential variables, and you are supposed to be able to solve x2 and u from the second equation, so you can substitute in the equation above. And this solving doesn't need to be analytical. It can be performed numerically. It has to be something as in principle, like I show in the next slide. For example, here you have that representation and you have some condition at the bottom, which talks about full column rank for this partial derivative. Of course, this condition translates into the need of solving x2 and u from the second equation, so you can substitute in the first equation and perform a simulation as an audit. This is actually a condition that helps you to understand whether a differential algebraic equation is well defined or it cannot be solved, let's say in a real-time system. Of course, we expect that if you have a system modeled in this way, it has to be with a solution. It has to have a solution, and it also has a unique solution. It cannot lead to some confusion. So the first condition to guarantee that is that you have a full column rank on that partial derivative, so you can solve x2 and u, at least numerically. Moving on this class of systems, which are actually differential algebraic equations of index 1, I will talk a little bit about index, differentiability index. It means the number of times you have to take derivatives of the algebraic equations, so you can convert the whole system into an ODE. In this case, it's an index 1 because you can actually solve x2 on u from the second equation, substituted in the first one, and obtain an ODE. So this is an index 1 differential algebraic equation. And we want to use convex control techniques. What does it mean, convex control? Convex control is a model-based technique. It requires rewrite in a nonlinear system, like the one on the left, rewrite it in this way, and then rewrite it as a convex sum of some, let's say, vertex systems of the form AIX, BIU, and these WIX are nonlinear functions that capture the nonlinearities in the original system. So these convex functions add up to 1 in some domain, and they are always between 0 and 1 in some domain. There is a very, very standard technique to rewrite a given nonlinear system into this form. It's a very standard procedure that I will show you later, at least briefly. And you can perform that if these functions are well defined in some domain. This domain, when you are asking for stability, has to include, of course, the origin. And convex control requires this structure so it can apply the direct Lyapunov method. And the direct Lyapunov method, as you surely know, allows establishing asymptotic stability of the origin with this condition here in the middle. So this is quite standard material. And the interesting thing is that when you use these convex representations combined with direct Lyapunov method, then you are allowed to obtain some linear matrix inequalities as sufficient conditions for analysis and design. The things that I showed in this slide are related with the stability only. So you can see here that the origin is asymptotically stable if you have a symmetric matrix, a positive definite matrix, which holds this inequality, which is very, very close related with the Lyapunov equation, when you put this expression equal to minus I. Of course, this condition is only sufficient because you are using the vertex matrices AI. These matrices arise from modeling the first nonlinear system as this thing on the right. So, well, this is the basics of convex control. This is just what we are aiming for. We are aiming to use convex control on differential algebraic equations of index 1, let's say. So what is convex control? Now we are going a little bit into detail. In convex control, you have a region of interest, let's call it omega. And in this region of interest, you have some nonlinearities, let's call it z of x. And these nonlinearities must be defined on this region of interest, let's say. If you have this, that means that you have also some maximum and minimum well-defined, some infimum and supremum in omega. Let's call it Z0 and Z1. If you have that, any nonlinearity of the form Z of x can be written as you see in this first equation. This W0 of x and this W1 of x are nonlinear functions that hold the convex sum property. This property means that you can put them together and add up to 1 for all x everywhere within the region omega and outside the region omega, as long as they are defined. And they move between 0 and 1 when you are in omega. So they are convex functions. They hold the convex sum property. Why is this important? Well, this is important because when you have several of them, like I show here with two convex sums, then you can stack together all these convex functions on the left side of this summation, and you can have these terms here. This can be extended, of course, to matrix cases or vector cases, as shown at the bottom of the slide. You can see here that you have two nonlinearities, Z1 and Z2 of x, that appear in this sum or appear in this product. And in any case, you can rewrite them as this if you have a convex representation of each nonlinearity. What does it mean? It means that the nonlinearities get captured in these convex functions, which are convex, I insist, in some region of interest, omega. And you have some constant matrices or constant vertices, which are here, that depend on those maxima and minima within the region of omega. So this expression will be used later when combined with the Dirac-Lyapunov method to obtain sufficient conditions for analysis and design. How is it done? Well, when you have several of them, you need a little bit of notation. So if you have many of them, let's say R of them in a region omega, then you have to define the minimum and maximum, the minima and maxima of these nonlinearities here. You have to construct the convex function as shown here before, and then you have some notation to index these indices here and these convex functions here. So you can put a multiple convex sum, let's say R of them, as shown here below, with these bold letters WI and bold letters I in this set of bits. So in this notation, the example that I put in the previous slide can be compactly written as shown here at the first two lines. You have these nonlinearities, you have this rewriting, which is using the convex functions WI1 and WI2, and you can put them together in this compact form here below. So you can have these vertices, AI, and you can have this composite convex function WI, and some vertices which belong to B2, which is the pairs of bits, 0, 0, 0, 1, 1, 0, and 1, 1. So actually you can rewrite a nonlinear expression in this convex form, and this can be done in a compact set of interest. Okay, so that means that when I have a model, let's say a nonlinear model, I can write it as a multilinear function of some nonlinearities Z, and then I can write each of these nonlinearities as a convex sum and put it together in this form. So why does it help? Well, because you can use a quadratic Lyapunov function after that, or any other sort of Lyapunov function candidate. I'm talking about the quadratic case because it's the simplest one. And if you take that and you take the time derivative, then you can use the convex sum property to put this convex sum at the leftmost side of the expression. So you can actually have the inequality here below if you want the system to be stable. And if you take into account that in the compact set that includes the origin, these functions wi are moving between 0 and 1, they are positive, and that you have this expression x transpose and x, then the sign of the whole expression can depend on the sign of these matrices in the middle. So you can extract sufficient conditions to guarantee this inequality and to guarantee that this function v of x is a genuine Lyapunov function. So you have this condition, p times ai plus ai transpose p, negative definite, and the other conditions, which is p positive definite. So you have a set of two inequalities here, two inequalities, which are linear matrix inequalities. So you, thanks to the convex representation, you obtain a set of linear matrix inequalities, which guarantee in a sufficient way asymptotic stability of the region. So what are the advantages of this form? Well, despite sufficiency, using linear matrix inequalities belongs to the convex optimization area. And convex optimization means that you can reach a solution or state that no solution can be found in a full way, in a polynomial time. This is a polynomial time problem, and there are many tools available in MATLAB or in some other platforms to solve this set of LMIs. So if you find that you construct some LMI conditions to warranty analysis or synthesis of controllers or observers, then you have the numerical advantage on your side, because these conditions, despite being sufficient, they can leave you, they can give you an answer in polynomial time, and they can give you, they lead to no local minima, in contrast with some non-polynomial time inequalities. Let's say, for example, many researchers publish papers which include bilinear matrix inequalities, but BMIs are non-convex, and of course you cannot guarantee that you find a solution. And if you find a solution, you cannot be sure that this solution is optimal. Whether on LMIs, using LMIs, you can be sure that these solutions are optimal. So this is a numerically efficient test using these LMIs. So you have sufficient conditions for asymptotic stability of a nonlinear system on a certain domain, let's say omega. So the same can be done for controller design, observer design, and many other problems, for example, H infinity, controller design, etc. Here you have a small slide about controller design, just to show you how you can do that. You have a nonlinear system, let's say an affining control nonlinear system like the one at the top, and you are searching for a nonlinear control law that achieves asymptotic stability of the region. So the system is rewritten as a convex sum with the techniques described before. So you can obtain this representation at the first equation here. And then you can propose a nonlinear control which uses these nonlinearities, this Wi of x, in the control law. So you obtain this here, which is a convex sum of some gains kj that you have to find. You have to find these gains. The closed loop system looks like this. As you can see, if you substitute u in the system above, you obtain this convex sum here, which is a double convex sum, but it is still a convex sum. You have, remember that for all x in omega, you have this sum equals to 1, and the Wi of x moves between 0 and 1. So if you work a little bit on that, you see that using the previous result on stability, you can have that system is asymptotically, has an origin which is asymptotically stable if these conditions hold. The inequalities above are not LMIs, not still, because P is multiplied by Kg, which is also a search variable, a variable of decision, a decision variable we say here. So we can perform some matrix manipulations to convert this inequality into an LMI, which is what happens here at the second inequality. Now this is an LMI on X and MJ. Once you found X and MJ, then you will have the controller, because you can solve Kj from this equality. Kj equals M times the inverse of X. So as you can see, obtaining an LMI condition for controller design or for observer design or for analysis, it's not so straightforward. Sometimes it is, like we show in stability analysis. Sometimes you have to perform some matrix manipulation in order to obtain a set of LMIs which guarantee the result. Naturally, every time you perform certain operations which are not invertible, you are restricting the domain of solution. So sufficiency is a source of conservativeness. And many works on convex control have addressed the problem of conservativeness. They try to obtain a set of LMIs which is more and more general, and that approaches necessity instead of remaining at sufficiency. So this has been the agenda, let's say, for convex control for a long time. Now, let's move on to differential algebraic equations. Though that discussion before was just about convex control in a standard way. So now we have to ask ourselves how to apply this to differential algebraic equations. So in this case, for differential algebraic equations, first I would like to talk about what kind of systems are addressed by differential algebraic equations. When you talk about robot manipulators, let's say kinematic chains of M-prismatic or revolute joints, you have the Euler-Lagrange equations. The equation at the beginning includes some friction here, like the partial derivative of the dissipation. You surely know this form. Also, you know the Lagrange-Euler form, which can be rearranged from the equation at the top. This is a set of second-order differential equations describing, for example, mechanical systems, which are fully actuated if these tau generalized forces have all these entries defined. And you can also have the very well-known technique of computer torque. In computer torque, as you know, you consider that all positions and velocities are available and that you have a perfect knowledge of the system model. So with these two elements, you can propose an inner control loop, this tau here, which cancels out all the nonlinearities like is done in exact feedback linearization. And then after doing that, you reduce your system to some linear one. And then you design this U with this proportional gain and this derivative gain, which are actually diagonal matrices. This is the standard computer torque control, which appears in many, many textbooks on robot manipulators. So when we are talking about restricted robot manipulators, what are we talking about? We are talking about configurations where some positions are fixed and the system has to adapt to that. I will show you some examples later, but in that case, every restriction, every position restriction, Ri of Q equal to 0, has to be incorporated in the model as a reaction force. These reaction forces are here represented as this sum because they are kappa position restrictions here, and they have to appear in the model. So nothing changes too much. But then we are faced with the problem of how do you simulate this sort of systems? In the other case, it is enough to use the usual tools, some Simulink file. You can put the equations, you can put some blocks if you want to use integrators and so on. You can perform simulation perfectly well. In this case, if you try to simulate this here, you are faced to several things. First, initial condition has to be consistent, which means that you have to hold the restrictions here, these position restrictions. So you cannot initialize the system whatever you want. You have to choose certain points which respect the restriction, because otherwise you are breaking the system. In addition to that, you have to hold these restrictions along the whole simulation, which of course there is no way to warranty in this context. Sometimes you can solve some states from the restrictions and substitute in the equations so you can reduce the differential algebraic equation, which is the case here, to some ordinary differential equations. Standard simulations in Simulink are ordinary differential equations. But this is not a very nice solution because it depends on solving analytically the restrictions or the variables to substitute in the differential equation. So we are faced with some trouble here. And in MATLAB, there are some solutions to that. We will discuss that later, but I will show you something a little bit more that prepares us to move to convex control. Well, if you want to follow some desired trajectory, let's say QD, and you are working on a restricted system, you can perform these LMIs here, which are very, very standard LMIs, just to solve the outer loop. That means U bar here. And you can use this computer tour, which is generalized for restricted systems. This is let's say, a very recent result, but it's not a very remarkable one. It's a very straightforward adaptation of the computer tour technique. And if you use this adaptation in certain plants, you have to simulate. Here, I am discussing a little bit about adaptation. For example, I'm saying how to select the physical variables that stand for differential states. For example, choosing the minimum number of positions in Q that allow describing the whole dynamics. Because when an Euler-Lagrange system is restricted, there are some set of variables which are actually describing the dynamics, and the rest of them are algebraic variables that can be solved from the algebraic equations and substituted in the other ones. These variables that can be solved are defined in x2, as x2 here in the second line. And as a third option, you have U as a vector gathering all the inputs in the system. Let's see this in practice. For example, here. I will go back a little bit later. This is a system where if you have no rail here, up here, then it will be like a double pendulum, a standard double pendulum, or a double arm robot manipulator, a two-link planar RR arm. So actually, it will be like a free one, which moves smoothly here. And you have two actuators, which are tau 1 and tau 2, and that will be it. But if you constrain this system to move in this rail, you have to take into account that thing. So you have these equations, which are exactly the same as in the standard Euler-Lagrange model. These equations come from the Lagrangian model and the kinetic energy and potential energy. This is very standard. And you have the dissipation terms for friction. This is also standard. And you have the reaction forces, which take into account the restriction. In this case, you have to take into account this angle, to take into account the coordinate frame, and you have this restriction, just one position restriction, which is described here. And as you can see, these restrictions is always an algebraic equation equal to 0, from which you can solve the reaction forces, which are here. And these reaction forces, you can put it here in this partial derivative, and you have these two terms that have to be included in the Euler-Lagrange model. This is all very well, but the problem is that then you have to simulate this system. How do you simulate the system if you have only these equations? Well, this is what is solved here. This is the way the generalized forces affect the system, because as you can see in the figure, you have three actuators. You have tau 1, you have tau 2, and you have this linear force F, which slides along the rail up here. So how to include these forces in the generalized force torque? This is described in this slide. You have the position of the end actuator, you have how the force F affects all these in the generalized torque, and you have all these included with tau 2. So you have tau 1, tau 2, and you have the resulting forces from the action of F. So this is the generalized torque. So after that, to simulate, you have a very interesting tool in MATLAB, which is the differential algebraic equation, the DAI toolbox, which is included with the symbolic toolbox, I think. So in the differential algebraic equation, you can include differential equations and algebraic equations without actually solving the algebraic part. If you solve the algebraic part and substitute in the differential one, you can obtain an ODE and simulate. And some variables you will obtain it from the simulations, and some others will be solved from the algebraic equations. But if you do that, you will be subject to consistent initialization that depends on you. You will be subject to holding these restrictions along the simulations, which also depends on the robustness of the ordinary differential equation. So it leads usually to some numerical problems. So I will advise against using this sort of procedure. I prefer to use the differential algebraic equation toolbox, because in that case, you define the differential equations, which if you go back to the image, you can actually see that if you know theta 1 and the angular velocity dot of theta 1, then you have the whole description of the system. I mean, if you know the position of the first angle and the velocity, the angular velocity of the first angle, then you have the whole system described, right? So theta 2 and the rest of variables here will need to adapt to that solution. If you know theta 1 and the time derivative, you know the whole system. What it means? Well, it means that the degrees of freedom in that restricted systems are lower than the degrees of freedom on a free system. So you have two differential variables, which are theta 1 and theta 1 dot. These form this vector here. And you have the rest of variables of the system as algebraic systems. Which are the rest of variables? Are theta 2, the angular velocity, theta 2 dot, and the accelerations, theta 1 double dot theta 2, and the Lagrange multiplier lambda. This Lagrange multiplier, remember, appeared here in the reaction forces, just right here. So each multiplier, Lagrange multiplier, is a new variable also. And the inputs can be renamed as U1, U2, and U3, this tau 1, tau 2, and F. So the dynamics are described here. These dynamics are very simple. Notice the simplicity. This is a linear system. But of course, this linear system is hiding the algebraic constraints, which are position constraint, the first derivative of the position constraint, which is the velocity constraint, the second time derivative of the position constraint, which is the acceleration constraint, and of course, the first and the second Lagrange-Euler equation. So we have two differential equations, which are right here, 5 algebraic equations, 7 in total, and this matches the number of variables in the system. 2 differential variables, 5 algebraic variables, 7 equations. So this is the same. And well, once you do that, you can perform the simulation in the DAI toolbox. It's not so straightforward, but it's a simple tool. And mainly, the simulation algorithm that actually performs the simulation of a differential algebraic equation is robust, which means that the algebraic equation is respected at all times. So the solvers are not the same as the solvers for ordinary differential equations. So I strongly recommend using that for simulation. Here, you will see the results of trying to track these signals. This is a reference signal for theta 1. So actually, the signal for theta 2 is implied, of course, by this. And then you can have this this simulation here. If all inputs are actuated, you obtain this. Here on the left, you see that you are actually tracking the trajectory. And on the figures on the right, you can see the control signals. And I would like to point out to something very interesting. You are fully actuated. You have actuators in tau 1, tau 2, and F. You are actually overactuated. But during this simulation, notice that tau 2 and F finally go to 0. And the only signal performing the whole action is tau 1. Why is this? Well, because the system is restricted, as we said. It's enough to move tau 1 to obtain all the desired trajectory that we want to follow with the N effector. So it makes sense. It actually makes sense to obtain these results. It also makes sense if you turn off one of these actuators, for example, tau 2, you put it at 0, and then you solve for tau 1 and F. Of course, you can perform the action exactly the same. It takes a little bit longer to track the signals on the left, but notice that it's just enough. So tau 1 performs the whole action, F goes to 0, and tau 2 was turned off, so it's 0 all the time. So, okay, here you have this computer torque. So if only tau 1 is available, the system has no solution. I mean, at least for the conditions, the linear matrix inequality conditions that I show at the first slide. But despite that, we can see that physically it has to have solution even if tau 2 and F are turned off. But this has no solution with those LMIs, which reminds us about the fact that LMI conditions are only sufficient. If you find no solution with some LMI conditions, you know nothing. You cannot claim that there is no solution to your problem. But of course, the source of conservativeness in this case doesn't come from the LMI itself. It comes from the matrix manipulations you made to obtain those LMIs and from dropping all the nonlinearities that were captured in Wi of x. Okay, so moving on. Now I will see how to use convex control for differential algebraic equations. This section is based on a very recent paper, which is mentioned down there, and it's available at the drive link that I provided at the beginning. So you can actually download the paper. It's not so difficult to understand. It's quite straightforward. After you see all these things that I have been discussing, it's quite straightforward. So if you want to use convex control, which means nonlinear control designed with LMIs and convex modeling for a differential algebraic equation of index 1, like the one described here, you will have the differential state, the algebraic state, the control input. We are going to consider nonlinear control laws of this form. K1 and K2 are nonlinear terms that use available information or available states. And I would like to stress up some very important part. Because x2 is involved in some algebraic equation with x1 and u, this means that if you use u equal to k1, k2 times x1, x2, some possible algebraic loop will appear, which requires solving u from the equation here. I mean, u is here, but x2 may involve u also through the algebraic restriction. So it has to be solved. And this gives a richer class of control functions because you can obtain actually rational control functions because it leads to some division here. So it gives a richer class of control signals. So the assumptions are the same. This first assumption means only that the whole system is index 1 and that you can solve x2 and u from the second equation. This is necessary to have a consistent differential algebraic equation. If this assumption does not hold, that means that the system cannot be solved in some domain. And the second assumption says that there are some matrices F1, F2, G1, G2, B1, B2, such that the index 1 differential algebraic equation can be written in this form, with all these entries well defined in some domain of interest in some omega. So this is a very, very easy assumption, which is easy to satisfy. It's not a big deal. And then we have the closed loop system. When we substitute this K1, K2 here, you obtain this, as you can see. And the origin of this system will be asymptotically stable if there exist matrices X1 constant, X2 and X3 possibly dependent on some parameters, with X3 being invertible, and some matrices M1 and M2 such that the following conditions hold. Where do these conditions come from? Well, they come from applying the Dirac Lyapunov method on this system and considering some generalized Lyapunov function. So these conditions here are not LMIs because they actually depend on the states. As you can see, F1, F2, G1, G2, B1, B2, M1, M2 are not constant. So we have to do some tasks to convert them into LMIs, but they are very close. So if you obtain a solution to these inequalities, you will obtain some gains M1, M2 and some matrices X1, X2, X3, and you can obtain the gains K1, K2 in this form. And obviously, any trajectory starting in the outermost Lyapunov level within the region of interest goes asymptotically to zero. So now, to obtain LMIs, we have to rewrite this nonlinear inequality as a convex sum of some linear inequalities. This is very well done with the previous methodology. You obtain all the nonlinearities in these places, and you convert them into this convex sum here. This convex sum now has constant F1, G1, G2, B1, B2, and then you can use it to propose some convex sum for X and M. So instead of looking for XK and ML, you are actually looking for the constant matrices here, XJK, MJL. So these are the affinite set of decision variables. And when you put all of these together in the inequalities, you obtain this here, and this is an LMI. You have the decision variables X1, X2, X3, M1, M2 with all these indexes J, and you have known matrices F1, F2, G1, G2, B1, B2, which come from convex modeling of the system. So these are LMIs which allow solving for K and K1 and K2 in the controller. This is, for example, this methodology can be applied to any system. I would like to insist on that. When I'm talking about convex control or computed torque for differential algebraic equations, I'm talking also about ordinary systems. That means ordinary differential equations. Any result concerning differential algebraic equations includes automatically ordinary differential equations. So, of course, you can use it for some system which is not restricted. You do not need to have a restricted system to apply the methodology just described. This is the case in this ball and beam system. This ball and beam system has a very well-known state space representation, a very standard one, which is an ordinary differential equation. The Euler-Lagrange equations are given here. You can see that. And you can actually rewrite that. Even this system, you can rewrite it as a differential algebraic equation, even if it has no restriction, no algebraic restriction. How do you do that? Well, you have four states, differential states, which are the position of the ball, the angle of the bar, and the linear derivative, the linear velocity of the ball, and the angular velocity of the bar. These are the four differential states. And you have two algebraic states, which are the accelerations, the ball acceleration and the bar acceleration. And in that way, you can actually write an index 1 die with these equations here. Notice that I have already factorized the system. So you have F1, F2, B1, B2, and G1, G2. So you can obtain a differential algebraic equation for this system, even if this is not a restricted one. So if you use that, you can actually take a region of interest, for example, the one described above. This region of interest concerns only the differential states because the algebraic states can be solved in terms of this. So here you have the possible nonlinearities. These z's are the non-constant terms appearing in these matrices. So here you have the bounds when you are talking about this region of interest. Here you have a rewriting of those terms with these constant vertices. And then you have the solving in the LMI toolbox. There are many of them. You have the LMI toolbox, which is integrated with MATLAB, which has a harder syntaxes and a harder writing coding like others than other solvers. For example, there is also the YALMIP interface. YALMIP is easier to use, but then you have these solvings, you have this solution, you have these controller gains, and you can solve U from the last equation. This equation is not solved yet because this K2 involves X2, which has also U. Here you have it, a little bit, or this is a little bit more detailed about how this algebraic loop appears. You have U, which is equal K1, X1, K2, X2. K1, X1 is not a problem, but K2, X2 can be split in two parts, the one concerning the first acceleration and the second acceleration. And of course, if you take into account the second acceleration, you see that the second acceleration has U. So you have U on the left-hand side and you have U on the right-hand side, which obliges to solve U here if you want to know the signal. I want to point out something very important. It doesn't mean that the methodology requires solving U. This is just to see the simulation result or to perform real-time implementation. But if you want to simulate and you do not want to solve U, it's perfectly fine because this algebraic equation can be incorporated directly in the differential algebraic equation toolbox because after all, this is another algebraic restriction. I don't know if I'm conveying the idea, but yes, so this U can be solved, of course, but you don't have to bother solving. If you put the equation right there, the solver will solve it automatically along the simulation. So it doesn't need to be solved. So this is a richer class of control laws because you see this rational term here. And this is the proof is not included here, but the thing is that this inverse here always exists within omega, within the region of interest. It doesn't go singular. So here you have some simulations about the time evolution of this control law when applied to the ball and beam system. So you see that you can achieve stabilization. And this is a second example, which is, let's say, easier in the sense that it goes more adequate to differential algebraic equations because it is a restricted system. You have this restriction here. It's very similar to the other one, so I will go a little bit quicker here. You have all of these. You have these differential algebraic equations and the restriction. Here we have to follow some constant reference. Here are the nonlinearities. Here are some gains resulting from the LMI solving. And it goes well when you want to reach some constant reference for θ1 and for the velocities. And here you see the inputs. These inputs, of course, don't go to zero because you don't want to go to zero. You want to go to some position which is not zero here. It's some fixed position. So you can see that you can perform actually convex control on a differential algebraic equation. Finally, I will talk about convex observer for differential algebraic equations, something very, very recent. There are two papers that we have published recently. The first one is on Kybernetica, and the second one is on International Journal of Robust and Nonlinear Control. I will present some general ideas. You have some differential algebraic equation of this form. So you have an output here defined. This is the same as before. And you can rearrange the whole thing in this descriptor redundancy form, which is the same thing. And with that descriptor redundancy form, you can provide an observer, which preserves the same shape and have some gains, some nonlinear gains, which depend on available signals. That means X hat, output Y, and input U. And with all those elements, you can construct a nonlinear observation error system like the one here, factorize the error signals in this form. And once you have the error, the observation error system here, you can perform Lyapunov analysis with this quadratic Lyapunov function, which is a generalization. It's a generalization of the standard one. Remember that we are talking about differential algebraic equations. So in this system, in this error system, the only differential variable is E1, whereas E2 and E3 are algebraic variables. So the Lyapunov function has to be stated in terms of the actual states of the system. The actual states of the system in these differential algebraic equations is E1. So you can actually use a Lyapunov function candidate just in E1. And if you want to involve E2 and E3, you extend the Lyapunov function in this form with this block diagonal matrix. So you can put P in this extended form. And you, instead of using E1 and E1 here, you can use E and E here. Of course, it doesn't make any difference for the Lyapunov function candidate, but it makes a whole difference when you take the time derivative. Because once you take the time derivative, you can involve the whole differential algebraic equation. That means the differential part at the first row, but also the algebraic parts at the second and third rows. So you have all these inequality, this expression here, and you can actually perform, let's say, perform LMI conditions from here. So you can check that on the paper. I don't want to extend too much on that. And I will talk a little bit about what we did in that last paper, the one just published in International Journal of Robust and Nonlinear Control, which is the same problem. You have a differential algebraic equation and you propose an observer, but we did not extend the thing, and we made it in a different way. The estimation error system is written in this way with new variables EF and EG, which have the difference between F and the difference between G. And the estimation error goes like that. And we incorporated another term, which is D here. And this D signal is called a compensation term. The original idea about a compensation term comes from Berger. Berger has two papers on observers of differential algebraic equations published in Transactions on Automatic Control. And in these papers, he proposed this compensation term, but he couldn't get LMIs for his analysis. And his examples have some trouble because he didn't care about the conditions for simulating the differential algebraic equations. If you remember the partial derivative conditions that I put at the beginning of the session, these partial derivative assumptions imply that the differential algebraic equation can be simulated. Berger ignores this, and the examples he provided cannot be simulated. So we took the idea of the compensation term and we used it to combine it with this form here that comes from Lyapunov analysis, incorporated in a different way. This is called something like the elimination lemma or Finso's lemma. And well, we incorporated this, and this is the way to perform controller analysis. All the algebraic part is in phi, and all the Lyapunov part is in p. And this is with some vector E bar extended, which includes this compensation term and allows to obtain some LMIs, but there are many other options. This is just one of those. So, well, this is it for me, for my part. Thank you for your attention. So I'd be glad to answer some questions. Sorry for going this far.
It's okay. Thank you. Thank you
Thank
very
you.
much. Yes, faculty members, researchers, if you have any questions, please unmute yourself and you can ask the question. The observer that we have designed is a full order observer or reduced order observer?
They have both. In the paper, in the last one, in the International Journal of Robust and Nonlinear Control, you have two cases. You have the full order observer and you have also a reduced order observer. You have both cases.
Okay.
Yeah, you can actually, I'm not sure if I'm still sharing the slides.
Slides are there. Yeah.
Okay, fine. Well, here in this estimation error system, when you have reduced order, you have less equations in the algebraic part, in this E2 part. So you can actually solve the reduced order gains and make the gains depending only on the available signals.
Yeah.
So yes, you have some reduced order observer there.
There is one question in the chat box. What is the index of this system of DAE?
The index is, well, if I have to say it in words, it's the number of times you have to take time derivatives of the algebraic equations to obtain an OD. Look, what is this? Is just right here. Let me show you. For example, in this slide here, the differential algebraic equation is here. But if you can imagine, there is there is a bigger family here, because you can have a function which depends on x and x dot and u equal to 0. So in that case, you cannot distinguish the algebraic part because it's just a function of the derivatives and that. So there are many classes. You have, in this case, you can solve x2 on u from the second equation and substitute in the first one. This is why it's index 1, because there is just one step ahead of becoming an ordinary differential equation, just one step ahead. The standard procedure to convert a differential algebraic equation into an ordinary differential equation is the Pantelides algorithm. The Pantelides algorithm was proposed in 1988, and it can handle differential algebraic equations of any sort. It consists basically in taking the time derivatives of the algebraic variables, the algebraic equations, sorry, and taking the time derivatives of all these equations as many times as you need to solve the missing variables, let's say the missing differential equations. The paradoxical thing is that when you have a differential algebraic equations, you have restrictions, you have less differential states. But if you want to simulate, you have to recover the missing dynamics. And these missing dynamics have to be solved, and they have to be initialized holding the algebraic equations. Once you do that, then you can perform the simulation as an ordinary differential equation. So the differentiability index, which is let's say the full name, the differentiability index of a differential algebraic equation, is the number of times I have to take the time derivative of the algebraic equations in order to convert the whole system into an ordinary differential equation. MATLAB has also a very, very simple example when you check the main documentation on differential algebraic equation toolbox, it has a single pendulum. But the model is completely different. It models the single pendulum with let's say with a position restriction. So it includes an algebraic restriction to say that the ball remains on some circular pattern.
Yes.
So this example is a second index 2 differential algebraic equations. And in that example, in MATLAB, they take the time derivatives to obtain the full example, the ordinary differential equation. So that's an index 2. But anyway, in any case, a physical system has to be consistent. That means that the differential equation description has to be reducible to some ordinary differential equation. Perhaps not easily, but it has to be like that. And the index, it's only a matter of how much pre-processing have you done. If you have, let's say, index 3 or index 4, it doesn't mean that it's a different differential algebraic equation. No. It only means that it needs some pre-processing before becoming an index 1 or an ordinary differential equation, which means index 0, right?
Okay. Yeah. Any other question? You can
Sir,
unmute.
what? Yes, sir, I have a question. May I?
Yeah,
See,
please.
yeah, sure.
Yeah, so what kind of properties in a physical system, can you please explain with an example? What kind of a property can lead to an index greater than 1?
Yeah, that's exactly what I was trying to point out. You don't need to hold any property actually, because well, first, if I show you the example here, let me see this. For example, this system is obviously a restricted one because it's not free. I mean, once you know theta 1, theta 2 has to be something. You don't have any option. So this system is a restricted one, and a differential algebraic equation model is suitable for this sort of system, restricted systems. But it doesn't mean that cannot be reduced to an ODE. It can be reduced to an ODE. And it doesn't mean that it cannot be expressed as a higher order differential algebraic equation. It can be a higher order differential equation because it is a matter of description. And all these descriptions are equivalent. If you have a higher order representation, it only means that you need more preprocessing in order to achieve index 1 or index 0. Index 0 meaning ordinary differential equation. This is why when I made the examples, you have some example like this, which is an ordinary differential equation, which is a very well-known model and has no restriction at all. So answering your question, you do not need any physical property for a system to be modeled as a differential algebraic equation. You can actually do it with any system. You can express any system model as a differential algebraic equation of any index, of any differentiability index. I wanted to show you something here. Let's see if I can find this die toolbox. Let me see. I want to see. Let me see. It can be, for example, deck ick. Let's see. Okay, this is something that finds consistent initial conditions. So I want to see the documentation for this, and this is a very interesting example, actually. Let's see. Well, I don't see it here. Differential algebraic equations implicit. Okay. Let me see. Differential algebraic equations. Yes, something like that. Yeah, I wanted to see the example. Well, I cannot find it right now. It's just an example of a single pendulum. maybe I don't know, maybe it's not here. Here you have the differential index, and here you have for
So
example.
we are not able to see the screen. We are able to see the PDF.
Sorry. Yeah, sorry. Let me share you. Whoa. Now I'm not sure if I can find where to do
It's
this.
okay. It's okay. It's okay. It's
I
fine.
think I just shared the presentation, right?
Yeah.
Yeah, but anyway, you
Yeah.
can find several examples at the MATLAB help,
Yeah.
and there you have an index 2 actually,
Yeah.
an index 2 example, which is a pendulum one,
Yeah.
and it's very simple actually to find it.
So one more question. So for
Sure.
this restricted system, so how when we are putting a restriction on a system and we are making a DAE, finding a DA and solving it the DAE, how is it different from making it an optimization problem with some constraint? How these two are different?
I think it's just a matter of robustness. For example, before using the differential algebraic equation toolbox, I made use of some how do we say, optimization algorithm to actually hold the algebraic restriction and simulate an ordinary differential equation. And with many systems, I succeeded actually to do that. You can obtain the same results as the DAE toolbox. But the problem is that robustness is essential here. And you can see that the algebraic restriction is drifting away from zero if you do not use some kind of robust algorithm for simulation. And I took advantage of the DAE toolbox because it was easier to use. Well, let's say easier in a sense. And overall, it's more robust. So if you use some optimization algorithm to simulate a DAE and to hold the algebraic restriction along the simulation, you can obtain the same result. But I'm not sure it can happen with more complex systems. I mean, I succeeded doing that with very low order systems, and when I go higher, it goes more complicated. It can also be because I'm using nonlinear control. And as you can see, when I use a control law or I use an observer, it's a nonlinear observer and a nonlinear control law, which includes a lot of nonlinearities. And many of them are captured in convex sums. So if I want to solve the linear matrix inequalities associated to that, it goes high, very, very high quickly, very, very quickly. So this is what they call the curse of dimensionality in this area, at least. So this is also a pending, let's say, a pending topic or a pending research topic, how to reduce this computational burden.
There is one question in the chat box. How about using the approach for non-affine configurations?
For non-affine configurations, it doesn't matter. When you have a non-affine structure, let's say, for example, I will put this here. Non-affine in control means that you have these here. You have this representation. Instead of obtaining this, you will have some WI here that includes X and U. That's the only thing that changes. This convex function will include the input signal in them. So it doesn't matter because actually the convex control approach that we presented just before, it has already an algebraic loop. So if the convex function includes some control signal, it doesn't matter because the algebraic loop is already there. So you can be solved from there, let's say explicitly if you are interested in seeing that signal, or implicitly if you want to simulate, you just put the equation that includes U on both sides of the equation, and the solver is robust enough to handle that. I mean, if it doesn't go for any singular value or anything like that, it doesn't matter. So non-affine systems can be handled in the same way, with that difference. These WI, these convex functions, may capture also some input signals.
Okay, thank you. Any other question? You can unmute and you can ask. Thank you very much.
Don't be shy.
I think there are no more questions.
All right.
So I'm very much thankful to you for accepting the
Thanks to
invitation.
you.
Yeah, and delivering a talk at 6:30 a.m. your local time.
It's
Because
not so early. It's a little bit on the early side, but it's just fine.
so thanks a lot, and maybe we can go ahead with some kind of collaboration in future.
Sure, I'm open. You have my email
Yeah,
actually, and so it's not a
yeah,
problem. You can contact me, and I answer quite promptly.
yeah. I
So
have
it's not
seen that.
a.
I have experienced that, and hope to see you in Kolkata for Indian Control Conference next time.
I wish. Yes,
Yeah,
I would like to go there. I hope.
yeah. Marine, can you take the charge? Yeah,
Sure, sir.
yeah.
So with this, we are concluding today's session. On behalf of Department of Electrical Engineering of KKWIEER Institute of Engineering Education and Research, and all the participants present here, I sincerely thank Professor Miguel Bernal for delivering such an insightful and enriching lecture on convex control. Your deep insights into nonlinear control, convex structures, and the case studies based approaches have given us valuable perspectives and understanding that will certainly benefit our research and teaching endeavors. We are grateful for your time, your effort, and the willingness to share your knowledge with us. I would also like to thank all the participants for their active engagement and thoughtful interaction during the session. With this, we are concluding today's session. Thank you all for being with us as a part of this FDP. And we will be having our next session on tomorrow, starting from 2 o'clock. So we will see in tomorrow's session. Thank you.
Thank you.
Many thanks
Thank you,
for the
Professor.
invitation.
Yeah, thank you.
Thank you. Have a nice evening.
Yeah, thank you. Yeah.
Thank you very much.
Bye.